to the understanding of it, and it's rather interesting. As I promised, when we have when we are dealing with minimizers or optimal curves of of time intervals increasing to infinity, you're gonna see that we are having the matter set as some sort of attractor, in a way that things gonna sort of get close to the matter sets, and it tells us quite some good qualitative properties about those curves. And you see now that there's an interplay between clearly that the dynamics and the PDE. I mean, it's still more. I mean, we are still more on the dynamic side because so far, I mean, I'm presenting it as so. Okay, so let's start. As always, stop me if you have questions or concerns. And today is Friday, so let's try to have it done smoothly and nicely. Okay, and again, concerns, let me know. So the goal is we're gonna do more about the peers barrier. Again, let me just record here. I mean, we have defined it, but just taking the time going to infinity, right? I mean, the length of the optimal curves is getting larger and larger. So you have X and Y. You can take as many curves as you like. Of course, I mean, but then, we are letting the length of the intervals getting bigger and bigger and bigger. And it goes to infinity, and we are wanting to take the lim inf, right? So the minimum possibly as the time interval going to infinity, I want to go from X to Y with this normalized action functional. So last time we have shown 4 points of the theorem. We have shown that the peer barrier is Lipschitz. We have shown that, if U is dominated from above, dominated by L plus C naught, then H, it's bounded from below by Uy minus Ux. We have shown that going from X to X itself is non-negative, right? We have shown the triangle inequality. So going, so going from X to X itself is always non-negative, right? So H of X is always greater or equal to 0. And then going from X to Y, and then from Y to Z is going to be always more expensive than going directly from X to Z, just the triangle inequality. Okay, so those are good. So we're gonna prove the remaining 4 points from 5 to 8 today, and I can say that 5, 7, and 8 are rather standard and straightforward. So 6 is the most interesting one. Okay, which tell me that although I'm going in the loop, going from X to X, by 3 is, we just said that it's non-negative. But if I were to have the point is in the projected matter set, then going in the loop in certain way is costing me 0. So it's essentially an equilibrium point or a stable point, right? It doesn't cost me so much to go there, right? So let's do it. Okay, so I also wrote that down here. So 5 is obvious, right? It's obvious. as we just use a triangle inequality, h of xy plus h of yx is going to be greater than equals to h of xx by triangle inequality, and this is greater equals to 0. Okay, so that's that. Okay, 6 is the fact that if we take x0 is in M0, this is the projected matter set, right? And we need to show that, the P barrier of XX is 0, right? And actually, I already described to you sort of the ideas earlier. Basically, roughly speaking, this is what it is, So if X is in the projected matter set, then you can essentially select a vector P of V so that XV is in the matter set, and because the matter set was so M0 is the projected to the torus of M tilde, and M0 tilde is the union of all the support of matter measure for mu matter measure. And we are taking the closure, right? And because we have proved that the P barrier is Lipschitz, so we can assume that, that XV is in support of some mu for a matter measure mu. Okay, so that's the first step. And now I realize that the matter measure, along the matter set is sort of invariance under the Lagrangian flow, right? And remember that that we also have, we also have that is invariance under the matter measure is invariance under the Lagrangian flow. So in other words, because of this, so again, so this is the point in the support of the matter set, and this is the Lagrangian flow. The measure is invariant under the Lagrangian flow, and also that not just that, but it's also because it's invariant, so it's measure preserving, right? So so because it's measure preserving by the Poincare recurrence theorem, then we can assume that let me just say it and then I'll state it. So the Poincare recurrence theorem tells me that then um, uh, the support of mu, or the recurrent points of the flow that is contained in the support of mu is dense in the support of mu. Okay, so this is essentially this is from the classical, measure theoretical result. So this is a Poincare. Yeah, okay, it's not correct. Poincare recurrence theorem. Let me just state it. If I have time, I prove it for you guys. Again, it's an exercise in measure theory. But basically, the Poincare recurrence theorem states the following: you have a measure space of finite measure X, and sigma is a set of measurable set. Mu is the measure. This is a finite measure space. And actually, let me state it and you can see it quite clearly. And let F mapping from X to X be a measure preserving map, a transformation. Then what it says is that for any measurable set is a subset of sigma, any measurable sets, we would have that the measures of all points in E such that there exists a point n in value n in n such that fn of e repeated n times fn of x is not in e for all n greater than equals to n, this set having the measure 0. Okay, so that's a Poincare recurrence theorem. What does it say? It tells us that if you take a point in the set E, then after a number of reiterations, you should revisit the set E. In other words, the set of point X in E, so that you don't revisit the set E after some iteration is having measure 0. So I mean, in a way, right? It's the recurrence theorem tells us that if this is your set E, and this is discrete dynamics, right? You do it just iteration in time that are natural numbers, if you wish. You take the set E here. You take point in the set E, right? You take this point and you do iterated it a couple of times, right? Maybe you have this is f of x. Maybe this is fx, this is fx. Keep reiterating. Eventually you should get to a point here in which you have fk of x is in A. So that's the Poincare recurrence theorem. And again, the proof is just let's say 2-3 lines. I bet that some of you here have done the proof by in the measure theory course. Essentially, you can imagine that if you take a set E and every time you reiterate, right, that it's going to create a set of the same measures. So if they are not intersecting with each other, then you're going to create a union of sets that are non-intersecting each other, and each of that has measure positive. So that would imply the contradiction because your space X is a finite measure. Okay, does it make sense? Any question for me about the Poincare recurrence theorem before I moved on? Any question or concerns? Okay, so as I promised, again, it's Friday, but if we have time eventually, by the end of the class, I'll prove for you the Poincare recurrence theorem. What it means is that essentially, you have a point in the, again, my picture is not good. I don't know how to draw orbits of infinite lengths, but basically what it means is that if you take a point, this point xv here, right? It's we can assume that it's a recurrence point, and recurrence point just means that so we just gonna assume that by the Poincare recurrence theorem, we can assume that we can, without loss of generality, we can assume that xv is a recurrent point of VTL. And what it meant is that the flow, it might not be periodic, but the flow is getting closer and closer to xv. If you take any small neighborhood around xv, right? So again, I mean, the definition of recurrence point is that if you take for any radius r greater than 0, the ball, then there exists a sequence tk going into infinity such that you would have phi tk of L of xv is within this ball xv radius r for any k in n, right? So you're gonna revisit that small neighborhood for an infinite number of times. Again, it's, if your orbit is periodic, then it's obvious you are just circulating in that orbit. Or this is also related to the example, the 1D example that I gave you the other day, right? So the 1D example that, that was this 0, this is z, this is 1 or something like that. The example was that if you start at a point x naught here, you're gonna go slowly and slowly to 0 along your backward characteristics. and you're getting as close to 0 as you want for large time. So 0 is a sort of stable point or a attractor, right? And your orbit is getting closer and closer to that. So it's a recurrent point as well. Okay. And that 0 was exactly the only point in the projected matter set. Okay. Right. And now you see the idea, right? So I have the point that is a recurrence point. I want to travel along the orbit, and I'm going to a point that is getting very close to that point, right? So it essentially gives me a loop, right? Not really a loop, but almost a loop. And then I'm going to close the loop by just, connecting the 2 points. And again, my picture was not good, but this was the point X. I don't know. Yeah. Yeah. Anyway, let me just write out the proof with you guys, and then we see. So you can find a sequence at tk going to infinity such that the projected of phi tkl on the torus is getting to x, converging to x. Okay. Um, and then I said that this limit is gonna go to 0, right? So why is it? Um, so we have the projected of phi LTK of xv is converging to x as k goes to infinity, and the action functional, right? Because we are on the optimal part, right? So integral from 0 to tk L phi SL xv ds plus C0 of tk, just gonna be the value at the beginning, the endpoints minus the value at the beginning point, right? So it's just gonna be u minus of uh, did I use mine? Yeah, u minus. So I'm respecting my notation. So u minus of projection of phi tkl xv minus u minus of x, right? And because we have this point inside here converges to x, right? So this one converges to x as k goes to infinity. So the whole thing converges to 0. So therefore, you see that we are going in a very long loop, but essentially we pay a 0 price. Okay, so maybe a let me try to draw a little bit better picture. I don't know, but let me try. So I'm going in a very long loop, but I'm getting closer and closer to x. So maybe this is exactly that. So this is the projection. Phi pi projected on phi tkl of xv. Okay, so we are getting closer and closer to each other. This is x. This is that point. So to close the loop, you just need to create a line segment connecting the 2 points, right? So you just need to close the loop by going then just close the loop by going from pi composite phi out tk close to x to get the loop closed. Okay, and that's exactly what we do. Yeah, I'm even lazy to write down here because I'm writing it down later. So once we close the loop, you see that the total amount of price we pay is epsilon plus epsilon, so it's 2 epsilon. Hence, the loop is closed, and then when we take lim inf, when tk goes to infinity, we have so then as tk goes to infinity, we deduce that h of x equals to 0. So we are done. Yeah. So that's exactly the ideas of sort of closing the loop and the ideas used in dynamics. And in fact, I told you that there was a Manet conjecture that is still open up to date, that it was probably only done in 2D. That they say is that generically there's always the matter set is is only one point or a periodic orbit, and the idea is actually from here, right? You can, you know, up to some perturbation, you can show that it's only one orbit. That's not too hard. And your orbit might not be periodic, so your orbit might going like this, so it has a recurrent point. So the idea then is sort of like to design things smartly in such a way that so you have a, so you have you know, let's say that the matter set has this is just for fun. So this is a let's say a discussion on the Manet conjecture. Conjecture that the matter set, you know, generically the matter set consists of only one point or one periodic orbit. And the idea is, again, I mean, the idea so far, if I know it correctly, the idea so far is rather simple. I mean, it's very technical to do it in 2D, and in general it's still open because it's not easy. But the idea is that you can deduce to that generically. Let's say that the matter set consists of one orbit, right? Let's say so. But your orbit might not be periodic, right? It can have recurrence points and stuff like that. So, you know, you are not periodic, but you're nearly periodic. So what you do is sort of like you go and not good, but anyway. So you keep sort of revisiting the point close by. Then the idea is that if you have 2 points that are quite close to each other, you would start with the Hamiltonian H. You would try to design some perturbation plus epsilon phi of x, and this perturbation has to connect the two point close to each other. Okay. 2 points close to each other. And that's essentially, so far, the idea I have seen in proving the Manet conjecture. What you do is that, again, you identify, you have to do it very smartly because you do a local perturbation and you have to make sure that you don't change the orbits outside. So you identify exactly those 2 points close to each other, and then you try to bridge the orbit to have a periodic orbit, or in the other ways, there's a cascade of doing so. You know, you have, you know, every time you're getting close to each other, maybe it's too hard to connect them right away. Then the idea is you make them getting further closer and then keep going in that orbit and getting them further closer. So, and after a finite number of times, you're really connecting the orbits, and that gives you a periodic orbit. And that's so far the only set of idea I've seen in the literature to prove this conjecture. But I mean, we are not going into that because we are still in a very general framework here. Okay, so let me finish the proof and then I'll stop for question. 7 and 8, this is also going in the same manner. You know, 7 is what? Let me go back to the statement of 7. So 7 tells you that, you know, you can define, you know, if you consider the Pierce barrier from X to Y, then, you know, by the definition, right? There would exist a sequence of minimizing extremal curves with time going to infinity that nearly approximate your Pierce barriers. The only difference is that again, it's just from the definition, right? Is that surely that the time is changing, but you start from X and Y. So that's just the definition. And there's not so much to say about that. And moreover, so 7 is just a definition, right? It's just a definition, nothing more than that. And for 8, what is just a little bit different is that moreover, if you allow flexibility, if you allow your curves gamma k to not really starting and ending from X and Y, but the endpoints converging to X and Y, then you can have the statement saying that if you have your starting points converging to X, ending point converging to Y, then you would have the inequality, right? H of xy is less than or equals to lim im of this action functional, and this is obvious as well. Why is it obvious? Because although you don't start and end at exactly X and Y, but it takes you just a little bit amount of cost or energy to go from X to gamma k of 0 and then gamma k of tk to Y. Right, so it just takes you a little bit amount of energy to go from X to that, and then from gamma, maybe let me say, so uh, take epsilon amount of cost to go from X to gamma k of 0, and then gamma k of tk to Y. And then, once you connect the two, and then you are done. And, I didn't write out the parts, connecting the orbits, because it's also written here. You just design a part of unit velocity going from X to gamma k of 0. Okay. And the key point is that the time it takes the alpha k is just the norm of the difference is going to 0. And similarly, you just take exactly the unit velocity curve to go from gamma k of tk to Y, right? And then when you take the difference, the price you pay is just the maximum of the Lagrangian here times with the time interval it takes, and you see that this is exactly the epsilon amount of cost it takes, right? So it's going to converge to 0 as k goes to infinity, and we are done. Okay, so let me stop here for question or concerns before I moved on. Any question or concern? Okay, no, yeah. So again, I mean, it would be a good idea to keep in your mind a lot. I mean, maybe I'm giving you out too much, but a lot of important open problems in the field. And also when I was writing the book, I did put in some questions at the end of each of the chapter to say, maybe this is some good question to, maybe this is some good question to be done and stuff like that. But I tried to avoid mentioning, big conjectures and stuff like this, because the book was supposed to be a textbook, so I didn't want to, make it, it's supposed to be more like useful for building the backgrounds. But when I'm teaching you guys here, then I'm happy to, describe the ideas and the things I know up to date about the state of the art. And you can see that sometimes the general ideas to do things is not too complicated. And so far up to date 2021, people can do only up to that. It's not because people are not smart, it's just because they're extremely smart and the subject is hard. However, with fresh minds and naive ideas, it often comes to great improvement and achievements in the field. So you should think about it that way. And myself, I guess I keep repeating it, that I believe in naive ideas, and I often try to come out with naive ideas. Many times it's wrong, but sometimes it works. Yep. Right. So now let me state the next theorem. This is exactly saying that, lemma. So this lemma, says essentially that this says that the matter set is kind of an attractor. Okay, it's a weak attractor. It's not an attractor in a maybe like in a weak form. Not a strong attractor in the classical Audi style, saying that you always have to converge to your attractor, or like circle around your attractor, blah blah blah, as time goes to infinity. It's not the case here. It's a weak attractor. So what does it say? It says that if you take V to be an open neighborhood of M0 tilde, so again, schematically, maybe this is just set M0 again. Maybe here. Maybe I'm trying to make it a periodic orbit. So schematically, you have this is your set M0, right? So you take a neighborhood around it. So just takes a neighborhood around it. Okay. So you would have this is V. It's a neighborhood of M0, right? And then the theorem says that for, you pick a neighborhood first, right? Let's say a ball of radius epsilon around M0. So an example would be that V is a union of all ball of XV radius epsilon, or XV in, for example, right? You just take balls around it. And then it would say that then there exists a time t equals to tv. So depending on the neighborhood, right, the time can get to infinity if the neighborhood is getting tiny. So it's a qualitative result, it's not quantitative. Again, yeah, the other thing is that give a quantitative version of this. Again, dynamical system, whenever you ask about quantitative results, it's mostly out of the scope of thing, right? So a quantitative version of this would be remarkable. Yeah. So there exists a time depending on the set V. In which way, I don't know. Such that you can see in the proof that surely we don't know. It's a compactness proof. Such that if you have a minimizing curve of time is a minimizing curve with time t greater than big T, then its orbit must get into V for some points. You see, it's not getting into V for all big time, but it's just it has to travel somehow into this neighborhood. Then there exists some S, so that gamma dot S is in V, right? So it's a weak result about attractor. Essentially, what it tells you is that you have your gamma 0 here, whatever, and it's sort of traveling around, but if time gets large and it has, so I don't know what happened. Okay. That your orbit has to travel to, inside the neighborhood a little bit. Okay. And that's the statement. The proof is rather standard. It's not easy, it's standard because we have devised a schematic way to construct matter measures. Okay, And you can see, you know, we're going to prove by, so the proof is proof by contradiction. I'm just going to summarize it, contradiction, and use a lifetime average to construct, yeah, I don't know, whatever, sorry, to construct matter measures. Okay. So that's pretty much it, the way we go. And you can see that if we go in the proof, then it follows exactly what we have done. So let me just do it quickly, and we have time for discussion. Um, you know, so assume by contradiction that you can find the time interval going to infinity and a sequence of minimizing curves so that you don't intersect with the neighborhood p at all, right? And time goes to infinity, we can assume time is always greater or equals to 1. And you know, when the time is big enough, remember that we're connecting 2 points that are not of, you know, again, gamma 0 and gamma t, we are in a compact setting, so the distance from each other is bounded by root of n at most. So exactly by the earlier result, we can prove that, you know, uh, the gammas are, uh, are fine. Of course, the position is also always in the torus, but we can also show that the velocity is uniformly bounded because we go for any time greater than equals to 1, right? So by Euler-Lagrange equations and also uh, conservation of energy and stuff like that, you can prove that this is always bounded. So clearly what you have is that gamma k dot in L infinity is always bounded by some C for all k in L, right? So that's sort of like about compactness. So we surely that have our curves, you know, in this in the space and velocity coupled together. They are sitting in a bounded or compact set. And here, you know, the process is exactly the same. We're going to construct the matter measures by assigning, you know, like the measures along the curve of each of the gamma k. So we would construct mu k, which is a probability measure, so that we observe that if we go along the curve, we and taking the average, right, we record it as m, the measure mu k. And as you guys have observed, for finite case, the measure mu k is just going to put the mass on your orbits, right? But it's going to be different when k goes to infinity, and the support of mu k is bounded. And again, I mean, with the boundedness, we are doomed. I mean, we can have mass travel to infinity. With the boundedness, we would need some tightness or something to have compactness of measures, right? But when we have probability measures and the support of them are in a compact set, then we can just pass the limit. You can assume by passing to a subsequence, then mu k converging weakly to mu. So support of mu is bounded. Mu is invariance under the Lagrangian flow. Um, and you can repeat exactly the same threshold, right? You know, blah blah blah. What is really important is that the Lagrangian acting on mu k, this integral is just, you know, 1 over tk, the function h of tk, right? Going from gamma k0 to gamma k tk. And here, everything kicks in, exactly the important boundedness result we proved last time. That is, you know, the normalized action functional is always bounded by from below by minus 2u minus L infinity, and from above by constant plus this one, right? You know, so it's always bounded. and once you have that, so we have like uh, like h of tk going from gamma k0 gamma k tk uh, plus c naught of tk. It's all about it between two constants, right? Minus c and c. Again, we don't know its limits, but when we take last time average, we divide by tk, then h of tk, 1 over tk, gamma k of 0, gamma k of tk, plus c naught is squeezed between c over tk and minus c over tk, right? Both of that surely converge to 0. So then you have this one, h of 1 over tk of h of tk, converging to minus c naught. Okay, so therefore when you pass the limit, you obtain that the Lagrangian acting on d mu is minus c naught, and mu is invariance under the Euler-Lagrange flow. So by definition of matter measure, mu is a matter measure. So you see it's a compactness result, right? And mu is a matter measure, fine, but this is contradiction, right? Because earlier we assumed that mu is devised from the gamma tk and gamma k, and gamma k has nothing to do with v. So gamma k is outside of v, right? Or maybe actually to make it precise, I should have said that its intersection with the closure of v is empty or something, or whatever. But then you deduce that mu is a matter measure, but the support of mu intersecting with v is empty, and that's a contradiction. So we are done. Yep. And you see that it's a same game. So same strategy. Of constructing matter measures as earlier. Okay. Right, so let me stop here for questions or discussions. Any questions or discussions? Any points you want to discuss? Yeah, I mean, to sum up, we can see that we have proved two important points. The first point is that if you have a point in the projected matter set, then the peer barriers going from that point to itself is 0. And the proof is essentially, you can see that you take that point and you go along the Euler-Lagrange flow. It's going to be a recurrent point, right? You're going to revisit it many times, and then the cost of going to along the orbit to a nearby point is almost 0, and then you just need to connect the two together to have a closed loop and having almost 0 cost. And when you let the time goes to infinity, the lim inf going to converge to 0. The second point is that the matter set, the invariant set is nearly, or I mean, or in a weak sense, an attractor, saying that if you take curves of length bigger and bigger, then it has to visit the a neighborhood of it, because if those orbits don't visit its neighborhood, then you can take the last time average of those orbits and pass the limit to construct a matter measures, and that matter measure has nothing to do with the orbit. So then you would arrive at a contradiction, right? And that's pretty much it for the whole two important points we have done today. Anything of concern? Again, I mean, and then I have not proved the Poincare recurrence theorem, but this is a very theoretical measure theory proof. I guess some of you have done it. I can prove it for you if you want. Any of you want me to do that, or? You're fine with that? Any question or concern? Yeah, you guys are quiet. Good. Yeah, I still have some time. So maybe let me just prove you the Poincare recurrence theorem, in 1 minute, and I'm done for the day. Okay. And again, it's Friday. The weather was nicer in the past couple of days. It's rainy now, but it's still fine. Get out for a walk, and again, keep distance with others, but try to have some fresh air and stuff like that. Okay, so let me copy the Poincare recurrence theorem and then try to give you a very quick proof. Okay, so this is the theorem. Let's see. Okay, so this is a Poincare recurrence theorem. So let's try to, oops, is it okay? So let's try to prove it. Again, I mean, the idea is very simple, right? If you have this is a set of measure positive, and if you don't visit it again and again, then you would have a lot of uh, a lot of disjoint sets of positive measures, and that would violate the fact that X, the matter set, I mean or the universal set in this case, it's only having finite measure, right? So that's exactly what I'm gonna do. I'm gonna define A of n to be just the union of k going from n to infinity. The pre-image f minus n of e. So I'm taking all the pre-images, right, of e. And what do I know? I know that again, A0, then what do we have? The first point is that A0 and okay, so F inverse of 0 is just going to be the identity. Okay, F0 by definition. So that means that A0 should contains E, right, at the very least, because F inverse 0 of E is just E. So that's the first thing. The second thing, I'm having that this is sort of telescopic. I mean, this is sort of decreasing, right? Because the more pre-images I take, the bigger the set. So I should have A0 contains A1, contains A2, contains so on and so forth, contains AN. It's telescopic, but what is really interesting is that if you take that, if you take what? If you take the pre-image of F inverse of 1 of a j plus 1, right? Then it would be the union F inverse 1 of the union k from j plus 1 to infinity F, this is fk, F inverse k of E, right? And this would be just k from j to infinity F inverse k of E, which is aj, right? So although that they are telescopic, but if you take F inverse of aj plus 1, it's going to give you aj. And because F is a measure preserving map, so this would imply that the measure of aj equals to the measure of aj plus 1. So then you have the measures, although they are, you know, like they are nested sets, right? A sequence of nested sets, but the measures of every set is the same. Of course, everything is finite because the set X is having finite measure, and we are nearly done because this would imply that finally then we would have that mu of E take away an, you know, it's less than equals, because E is maybe even smaller than A0, right? So mu of A0 take away an, which is zero measure, right? Because again, they are nested sequence, but each of them having same measure. And this would imply that mu of E taking away the whole the least amount, so just the intersection of n from 1 to infinity, is just going to be less than or equal to summation of n of mu of E take away an, which is still 0. Okay, so I have this measures of E take away this whole union is having measure 0. Okay, and I'm done, right? Because E is and what are the points here? So this is exactly what we want. As X is in E, take away the intersection of an, if and only if X is in E, right? And X is not in the intersection of an. And X is not in the intersection of an if and only if X is in E, and maybe X is not in a big N for some N. Big N. And you recall what's the definition of an? Where is an? An is the union here, right? Union of all F inverse of E. So if X is not in the union of everything, then that means that X is in E. And F of K of X is not in E for all K bigger than or equals to N. That means that, you know, you're not going to revisit the neighborhood, you know, for all iterations big enough, right? And that's exactly that. So we have shown that if we take away all those points and we are left with a set of measure 0. Get that? Okay. And this is a measure theoretic proof, but it's very important, you know, in dynamics, also in probability, you know, Borel-Cantelli style, and you know, whatever. Okay. Yeah, I think I'm over time, but any quick question or concern, or else we can have a good weekend. I mean, after finishing the duty of today, stuff like that. Questions, concerns? Okay, great. So thank you all, and then have a great weekend. And stay safe and healthy, and you know, I'll see you on Monday.